Hi there, this is a follow-up to my previous video where I showed you that there is a sequence of moves on the Rubik's Cube which you have to repeat exactly 1260 times in order to restore the cube. So this number is called the order of a sequence. So every sequence of moves has this number. Say if you do U, the order is 4 because you have to do 4 times U in order to restore the cube. Say the sexy move here, this has order 6 because when I do it 6 times, I have restored the cube. And what I showed you in the video is that there is a sequence of moves whose order is 1260. And what I also claimed is that this is the maximal order you can achieve. So there's no sequence of moves whose order is, say, 3000 or something like that. And many people have requested a proof for this, and this is what this video is about. So I will prove to you that the order of every sequence of moves on the Rubik's Cube is at most 1260, and in the previous video we also saw that this is achievable, so this is actually the maximal order then. And the proof that this is the maximal order will require quite a bit of mathematics, but no worries, I will explain every concept necessary. So we will learn something about permutations and cycle decompositions, which actually is also useful to understand the cube in general. So it's useful to learn this also for other questions related to the Rubik's Cube. If you're already familiar with these concepts, you can just skip to the next section. So I will provide timestamps in the video description. So the rough outline of the video then is as follows. So first of all, we will find a mathematical model of these sequences of moves here. So these are namely just certain permutations. And then we will study these permutations quite a bit, and then we will use all of this theory to reduce the problem to find the maximal order to a problem in number theory. So this means that we just have to find certain numbers which behave in a certain way, and this could actually be done by hand, but I've decided to just write some code. We will also look at this code then together, and this solves the problem then for us. Okay, then let's start with the theory of permutations in the context of the Rubik's Cube. So as you see, we have 6 faces, and each face has 9 facelets, as you call them. So there used to be stickers, but nowadays you usually have stickerless cubes. These are just the squares here, which have individual colors. What you do when you do moves is that you move these facelets around. This is basically happening. So for example, if I do the move U, this facelet goes here, right? And if I do the move F, this facelet goes here. And also with combinations of these single face moves, so for example, if I do RU, this facelet goes here, right? So this is what's happening. So we have 54 facelets, so this is 6 times 9. And if you do any sequence of moves, you basically permute these facelets. And a permutation is just a very fancy term for a way of rearranging objects, which were in a sequence before, and after permuting them, they are in a different sequence. So for example, if you have ever shuffled cards, you have basically permuted the cards, and this is what's happening here as well. Let's make it a bit more formal to also analyze this mathematically. So a permutation is a certain map. So we first have to define what a map is. So a map, or a mapping as you also call it, is written like this. So you have 2 sets x and y. For us, a set is just a bunch of things. In our case, it's always the set of facelets or cubies. And this map is called f. So you say that this is a map f from x to y. So what is this thing here? It's just a way of assigning to every element of x a new element of y. So it's an assignment that maps each element of big X. So this is how you draw elements of these sets, so the pieces contained in these sets. And what you get out is an element of y, and this is how you denote it, f of x. So this is almost the same as a function, but functions usually are used in the context of sets of numbers or functions. A map is a bit more general, but essentially it's the same. So if you know what a function is, a map is the same, but the sets here can be very abstract. In our case, the sets x and y are the same, namely the sets of facelets. So we assign to every element of x a new element of y. This is a map. And now we have to say when a map is bijective. So a map is called bijective when every element of y is hit by exactly one element in x. So what do I mean by this? So when for every element there is exactly one element in x, so that x is mapped to y, with y equals to f of x. So you see that this means two things. So first of all, when we map these elements from x to elements of y, we get each element of y when it's bijective, because we have for every element of y a pre-image, how you call it, so an element of x which hits the y element here. But this assertion here, there is, so sorry, this is a bit hard to read here, there's exactly one. So this means that it's also uniquely determined. And how you can envision this, so let's say we have here two bags representing our two sets. And as a matter of fact, if there's a bijective mapping here between these two sets, they have the same number of elements. So let's draw 5 elements as dots here in some way into these sets. And what a bijective mapping is just a way of rearranging the elements. So let's say this element is mapped to this one here. Let's say this one here goes to this one. And notice that I am not allowed to draw this arrow also here, because then we have not the uniqueness here. And then let's say this goes here. And then we have only 2 left. So let's say this one goes here. And then the remaining one has to go here, right? So this is a bijection. You just associate the elements in a one-to-one manner. So every element of x belongs to exactly one element of y, and also vice versa. So every element of y corresponds to exactly one element of x. So this is the idea of a bijective mapping from x to y. And then you can also invert it. So every bijective map has actually an inverse map, f to the minus 1, which goes in the other direction. So there you just invert the correspondences here. All right, and permutations are just special bijective maps. So this is why I have explained this now. So permutation is just a special case of bijective map, namely when the second set is equal to the first one. So it's a bijective map from x to itself, right? So this looks like then this. Let's say we have here our set x. Let's again draw 5 elements here. And then say we map this element to this one. We map, say, this element to this one. This to this one. Here, let's say this goes to this one. And let's say this goes to this one. So here, this is how it could look like. So here we have 1 3 cycle, but we will talk about this also later, and 1 2 cycle. So in a formal way, if you want to name these elements A, B, C, D, E, this mapping here F, this is characterized by f of A is C, f of C is D, f of d is a. So this is our 3 cycle here. And then we have a 2 cycle, f of b is e, and f of e is b. This is the 2 cycle. And in our case, the set X is the set of facelets. So on each face, we have 9 facelets here. So this means that in total, we have 54 facelets. And a sequence of moves is just a very special way of permuting these facelets. So in our case, so example, X is the set of facelets on the Rubik's cube, and F could be a sequence of moves. So again, let's have a look at a simple example. Say the sequence of moves RU. This maps this facelet to this one here. And this facelet is fixed, so actually we don't have to consider these center facelets for the purpose of this video, because we will only look at moves like R, L, U prime, D, etc. So I don't allow these slice turns here. So this means that for the purpose of this video, these center facelets can be basically ignored. And for example, this facelet, when I do RU, this goes here. And a very important property of sequences of moves is that you can compose them. So if you do a sequence of moves, say RU, and you have another sequence of moves saying F, you can just do them after another, right? And this also can be done with permutations in general, or actually maps, but let's restrict to permutations for now. So if I have 2 permutations F and G from a set X to itself, we can have a new permutation. Let's call it F times G. So we treat it as a product. So this is again a permutation. And how do you define it? So in order to make this a map, you have to say, if you have an element small x and big X here, what is the image? So where does it map to? And now we first do F and then G. So I first apply F to this small x, and then I apply G to the result. By the way, this is different to mathematicians usually do. You also see that here the sequence has changed, F, G, X, G, F, X. And usually, so this is just a side note, you define this in the other way around, in mathematics at least. But in the cubing community, you don't do it this way, right? When you read F times G for 2 sequences of moves, you want that you first do F and then G. So this is why I did this here in this order here. And you can easily check this is still a permutation if F and G are permutations. So this is not what we're doing here. And there's also a very special permutation, namely the identity, which is called it, with the X here as an index. It's very easy. It's the simplest permutation you can imagine. Namely, just takes every element and maps it to itself. So as a sequence of moves, this is the following sequence. Done. It just consists of 0 moves, and of course you can also do this. Okay. All right. So these are the 2 basic operations we have for permutations. And actually we have a third one, namely I already mentioned that you can always invert these, but we will not need them in this video here. Now we can formally define what the order actually is. So first of all, if I have a permutation and any natural number, so 0, 1, 2, etc., I can define the power, which is again a permutation, and it's just defined recursively as the iterated product. So for example, this one here is F times F. This one here is F squared times F, which is again then this one, etc. So for every natural number you can define this, and by convention F to the power of 0 is the identity, and F to 1 is just F. All right, so we define these permutations here, and then the order of F is the smallest positive natural number, so 0 is not allowed, with f to the power of n is the identity. This doesn't have to exist, but if x is finite, this always exists. And in our case, these sets are always finite. For example, here we have 54 facelets, so of course this is a finite set then. Alright, and now we have to define the relevant moves we want to consider. So again, we have the set of facelets on the Rubik's cube, and we have special permutations. For example, u, this is the permutation of the set, right? The move u, this maps, for example, this facelet to this one here, this one here, and this one here again. When I do this, this one stays fixed, and for example, this one goes here, right? This one goes here, this one goes here, this one goes here. So all the other ones here in the bottom are of course fixed. These are fixed points, but in any case, we see that this is actually a permutation of this set of facelets. And in the same way, you can also define it with every other basic face move. So for example, we have D, so the down layer, and we also have R, L, and also the front layer move and the back layer move. These are also permutations. And the sequences of moves which we consider are those which can be built up from these. So let's call it G. So these are all products of sequences of moves. S is any number you can imagine, where each Fi is one of these face moves. So for example, U, D, R, L, F, B. And if you want to, you can also take U prime here, but it doesn't matter because U prime is just U cubed, so you actually don't need to take the inverses here as well. So this is the sequence of all moves which we consider to be analyzed, and it's called the Rubik's cube group. What a group is, I have explained in another video, but this was in German. So if you're interested, I can also make another video on group theory in English. But for the sake of this video, you don't need to wonder about this term. It's just important that we know what we're talking about. So we're just talking about every permutation which can be built up in the sense of iterated products from the basic face moves. And now we can actually state what the goal of this video is. So we have the theorem. If F is any element of G, so every sequence of moves we consider, then the order of F, and this makes sense because F is a permutation, is at most 1260. And remember, in the last video I already gave you an example of a sequence of moves whose order is exactly this. So this means that we're then done. We have found the maximal order in this group. Alright, the next step is to make the problem a bit more easy by decomposing the facelets into certain types. So as I mentioned, I don't want to allow these slice turns, so this means that we can just ignore the centers, and I will not talk about them anymore. We'll just have to look at the corners and the edges. So each edge consists of 2 edge facelets, and each corner consists of 3 corner facelets, right? And when we permute the facelets, we also permute the pieces. So for example, if I do U, of course this corner goes to this one, and this corner goes to this one, this here. So it's a 4 cycle. We will talk about this later. And also with the edges. So for example, the move R moves this edge here, right? Etc. So what you see is that with every sequence of moves, you can actually generate 2 permutations, maybe one permutation of the edges and one permutation of the corners. So let's write this down for a moment. If I have an element of G, and remember G is the set of all sequences of moves on Rubik's cube, Then I have two permutations. Let's call it Fe. It's a permutation of the edges and also a permutation of the corners. And this makes the problem quite simple, namely we have just 12 edges and 8 corners. So in total we just have to consider 20 pieces, and it's much simpler to analyze these permutations then, because here the sets are much smaller. So let me write it down. There are 12 edges and there are 8 corners. And now we need to remember what we did in the last video, namely we showed that, for example, if I do the sexy move 2 times, you see that all corners are in the correct position. So this means that the corner permutation is the identity. This doesn't mean that the permutation has solved the corners, but if I do it 3 times, of course it will be solved, because when the orientation is wrong but the position is correct, I can solve the orientation by just doing it 3 times, at most 3 times. So with the edges it's the same. So if there was an algorithm which flips 2 edges and you have repeated the algorithm already, let's say 10 times, if you do it another 10 times, you have flipped these edges again, so you have restored the whole cube actually. So this means what we can then now conclude is that we have the following, or claim, or observation if you want to. The order of f is at most the least common multiple, I will say something about this later, of the order 2 times the order of the edge permutation and 3 times the order of the corner permutation. So why is this the case? So first of all, here in this permutation of the edges, we don't consider the orientation of the edges. So if we have solved the position of the edges, we are not done yet. So we have to do it 2 times in order to restore also the orientations. And it's the same with the corners, because here we have 3 possible orientations. And if we flip these corners in some way, if we do the same procedure 3 times, then we have also restored the orientations. And the whole cube is restored when we have solved the edges and the corners. For example, if you have restored, let's say, the edges after 12 moves, including the orientations, and the corners, let's say, after 30 moves, when do you have restored the whole cube? Well, you just have to solve the edges again, let's say after 24 moves, right? Then again, so it's always a multiple of 12, right? And also here, the corners are also solved after 60 moves or repetitions. Actually, I mean repetitions of the same permutation here. And then also after 90. And what you're looking for is a multiple of both of these numbers, because this is a multiple of 12, this is a multiple of 30. So we have to look for a multiple of 12 and 30. And you can compute this easily. And then you have restored the edges and the corners actually. And this is why we have this estimate here. And why don't I have equal? Well, the thing is that the multiplication with 2 here was just for security reasons. There could be an algorithm which actually restores the orientations as well. So for example, if I do the U-perm, I have permuted the edges and I don't have to repeat it another 2 times in order to restore them, right? So let's say I have this situation, I just have to do it 1 time, right? So this multiplication with 2 here is not precise. It could mean that it's not necessary to repeated again as many times, and also the same with the corners. So this is why we have here not the equal sign, but the less than or equal sign. So this is very nice, because now we just have to find the maximal order which can appear here, and then the maximal order which can appear here, and then we can plug it into this formula here, and then we have an upper estimate for our order. And remember, we just want to get this estimate here, and then this will be done. But actually, this is not quite true, because the reason is that these permutations here are not independent from another. So, for example, maybe you know, and actually we will prove this later, that you cannot just swap two edge pieces on the cube. You can, if you want to, do a T-perm, and this flips two edges, but also two corners, right? So this is a sign that these permutations here, the edge and the corner permutation, are not isolated from another. And as a matter of fact, if you ignore this connection, this estimate here will not be good enough. So this is something we need to address later. All right, and what we do now is to make a more fine-grained analysis of these smaller permutations here. And for this, we need to talk about cycles. So a cycle is a very easy permutation, namely it just cycles around some number. So if I have a set here, x, let's say again it has 5 elements, and you just cycle these elements around. This is a cycle. In general, let's say you have a set x which consists of numbers x1 to the xm, let's say. So in this case m was 5. Then you have a special permutation which just maps the first one to the second one. So this here is another way of writing this relation. Then the second element to the third one, etc. Then the second to last element to the last one. And then we have the cycle, so the last element goes again to the first element. So for example, in this case, we could denote the elements like this here. So this is how the cycle looks. And there's a very short way of writing this, namely f is then written like this here. So for example, if I have this cycle here, this maps 1 to 2, 2 to 3, and 3 to 1. So this is a permutation of the numbers 1 to 3, which is this cycle here. Remember, in the first example of a permutation, we had this kind of picture here. This is actually a product of two cycles. Let's name these with numbers here for the sake of simplicity. And then this is the following permutation. It consists of a two cycles, so 1 is mapped to 2, 2 is mapped to 1 here. This is the two-sided arrow. And here 3 is mapped to 4. 4 is mapped to 5, and 5 is mapped to 3. So this is a product of two cycles, and they are disjoint. What do I mean by disjoint? It means that the numbers appearing in this cycle don't appear here. So for example, this is not a disjoint cycle. By the way, you can also compute this here very easily in this cycle description. So here 1 goes to 2, and then here 2 goes to 3, 3 goes to 2, and 2 goes here to 1, and then stays here. So this is actually a product of two cycles. Here in this case, it's just a 3 cycle. So you can also very easily compute with these cycles. And this was actually not a coincidence that this permutation was a product of disjoint cycles. So this is the theorem here, which I need to just use without proof. So every permutation of a finite set is unique, actually, product of disjoint cycles. So for example, let's say I have the set X and it consists of the numbers 1, 2, 3, 4, 5. And let's make a map like this here. I just try to randomly generate a permutation. So what happens here, when I look at this, I can start the cycle with 1. 1 goes to 5. I draw this here. 5 goes to 2. 2 goes to 4. 4 goes to 3. And 3 goes to 1. This is actually just a 5 cycle. So if I have another map, say another example, let's do this one here. So what happens here is, so this was F, so 1 goes to 2, 2 goes to 1, so this is a 2 cycle, 3 goes to itself, so this is just a 1 cycle, this is also possible, and here we have another 2 cycle. So this is very useful. So this means that oftentimes when we study permutations, we just have to study the cycles individually. Now let's have a look at how these cycles look like at some examples on the Rubik's Cube. So for example, we have the sequence of moves U, and remember we have associated 2 permutations with this. So one is with the corners and one is with the edges. And let's denote the edges now, the set of edges with E1 to the E12. And the corners, we have just 8 of them, C1 to C8. So, and the way I will denote them is as follows. So let's face white on top and green on front here, and I have denoted them like this. So in the top face we have C1, C2, C3, C4. And then in the bottom layer here, we have here C5, C6, here's C7, here's C8. Okay, these are the 8 corners, and then we can already write down what UC is. So UC, what is happening here is just a 4 cycle. For example, C1 goes to C2, right? C2 goes to C3, C3 goes to C4, C4 goes to C1. So this is actually this 4 cycle here. We can also do it with R, for example, here. When I do R, C8 goes to C4, C4 goes to C3, C3 goes to C7, C7 goes to C8. So this is R as a cycle of the corners. And now for the edges, I have denoted them like this. So on the top we have E1, E2, E3, E4. Then in the equator we have E5, E6, E7, E8. And then in the down layer here we have E9, E10, in the back E11, and then here in the right E12. So this is just a random numeration of the edges and corners. Which one we choose doesn't matter, but I wanted to have a reference point, and this is what we choose now here. So when I do U, for example, this is also a 4 cycle of edges. So E1 goes to E2, right? E2 goes to E3, E3 goes to E4, E4 goes to E1. So this is actually very similar here. And with all face moves, you realize that this is always a 4 cycle of the corners and the edges, right? So for example, if I do L, it's also a 4 cycle of these edges here. Yeah, let's have a look at a more complicated example, namely the sexy move, which we can abbreviate by S. So what is the permutation of the edges and what is the permutation of the corners as a product of cycles? So I will hold green in the front, white in the top, and let's do the sexy move. So you see that E1 didn't change, E2 also not, but E3, this has gone elsewhere. This has gone here where actually E8 was. So this is here a cycle starting with E3, and this goes to E8. And the E8 corner, so green, red, where did this go? This went here, which is actually E4. So the cycle continues with E4. And then E4, this went here to E3. So this is where actually the cycle is finished. And every other edge here is still the same. For example, this one, this one. So this means that we're done here with respect to the edges. And now for the corners, we see that this corner here is fixed. So it's just a one cycle if you want to. Actually, oftentimes you don't write down the one cycle. So you could also just omit the cycle from the cycle decomposition. Next up, we have C2, which was here, which has moved somewhere else here. So C2 has actually moved to C3. And C3, this has moved here, where C2 was. So actually, we have a two cycle here. These two corners have been switched here. And what about C4? So here was C4. This has moved here, where actually C8 is. So we have another cycle beginning like this. And the C8 corner has moved here, where C4 was. So this is again a two cycle. All the corners except for these are fixed. So for example, C6 is still in the same position, C7 as well, and C5 as well. So we can just write a bunch of one cycles or omit them as mentioned. So if you want to, you can just abbreviate it like this here. So this is the cycle decomposition of the sexy move. And now let us do the same for the sequence of moves, which actually we already know has order 1260. This is not necessary for this video, but I think it's a very good exercise which brings all these concepts together. So this was R, U2, D prime, B, D prime. So what is here? The sequence or the permutation of the edges and the corners. So this is what we write down now. Let's start with the edges. So first let me do the move one time here. Let's have a look. So indeed E1 has moved, it's not there anymore. E1 is now here. So this is what E6 was. So the cycle starts with E1 goes to E6. E6 has gone here. So this was denoted E12. The next E12 went here, so this is E8. And E8, so the green red one, has moved here, which was E2. And then E2, where did it go? Is here. So this is E4. And now E4, this went here. So this was actually E3. And E3 is here, so at E1. So this means that we have completed the cycle. It's actually a 7 cycle of edge pieces here. Let's have a look at E5. So this is fixed. I won't write it down here. It's the only edge which remains fixed by this sequence of moves. This is also why you saw in the video that this portion here was always not changing at all, but the rest was indeed changing. What about the next one, which hasn't been covered yet, which is E7? So E7 moved here, which is actually E10, the position of E10. So let me continue here. E7 goes to E10, and E10 has moved here, which actually was the position of E7. So it's a 2 cycle again. And then E11, this is swapped with E9. So E9, E11. So we have two cycles and one 7 cycle as for the edges. So what about the corners? So it's a bit more easy here. For example, C1, this went here to C2. C2, where is it? Has moved here to C4, and C4 is now here. So it's a 3 cycle. Okay, so what about C3 here? This is now here where C5 is. And C5, this has moved here where C8 was. And C8, where is it now? This is here. So C7. And then C7, this is now here. So C6. And C6, this is now here. So we have completed the cycle, and here we have actually used all of the corners. So the corner permutation has no fixed points in this case. So we have a 3 cycle and a 5 cycle. So we will come back to this later, because this is actually the cyclic decomposition which is responsible for the highest possible order you can achieve. So basically our task is to actually prove this, but more on this later. And notice something about these cycle decompositions. So if we now also denote the fixed points, so for example here we had E5 as a fixed point, you notice that the numbers of the lengths, so here with AE, it's 7, 2, 2, 1. When you sum up these numbers, right? So the sum of these numbers is 12, which is clear because we kind of have to distribute the 12 edges on these cycles here. So it's clear that the sum of these numbers must be 12. And here it's also clear that the sum with the corners here, it's 8. So sum of 3 and 5 here, this is 8. So this is a kind of fancy way of writing this sum here. And this is just 3 plus 5. So whenever you decompose actually the edge permutation or the corner permutation of any sequence of moves such as this one, you end up with certain cycle lengths which add up to 12, respectively 8. This is something we need to keep in mind. So whenever we have a sequence of moves F in our group G, then the edge permutation decomposes into a product of cycles, so disjoint cycles, of course, of lengths, say N1 to Ns, and also Fc. So the same with M1 to Mt. And what you then observe is that the sum of all of these numbers here is 12. And the sum of these numbers here is 8. And this is clear because, again, we have 12 edges and they have to appear in these cycles exactly once because they are disjoint. And of course, when one of these numbers is 1, it means that it's a fixed point. So this is also allowed. And with the corners, it's the same. So every corner has to appear in exactly one of these cycles, no matter which permutation you take, right? So the sum of the cycle lengths here has to be 8. So this is one step closer to what I mentioned in the beginning of the video, namely that we will reduce the problem to a problem which is just number theory. And here we already see it. So we have to find certain partitions. So this is how we call such a sum decomposition here of 12 or 8. Okay, and the next step is to find a formula for the order of these edge and corner permutations, which just depends on these numbers here, which is of course very useful and another step towards this reduction to a number theory problem. So to achieve this, we first realize that the order of a cycle, let's say 1, 2, 3, is just 3. This is of course very clear when you have this cycle here. And you repeat the cycle 3 times, you end up in the permutation, which does nothing. So the identity permutation. And in general, if you have a sequence, a cycle of length m, and take the order. This is just m. It's very easy to prove, so I won't give you the formal proof, and it's also clear intuitively. And when you now take any permutation f, we remember that f can be written as a product of disjoint cycles. So let's do this. So these are disjoint cycles, and because they are disjoint, it's easy to see that this is just the least common multiple of the orders of the individual cycles. Because basically, when you take a power of this permutation, you can just put this exponent here inside, because these permutations are disjoint. And in order for this to be the identity, again, because these permutations are disjoint, every single of these has to be the identity, and then you can achieve this formula here. This means that if I have a permutation which is the product of cycles of lengths n1 to, let's say, ns, then we know the order. That means just the least common multiple of these numbers. So LCM of n1 to ns. So this is very useful. So for example, when you look at the sexy move here, you have two cycles. The least common multiple of 2 and 2 is just 2. So this means that here the order of this corner permutation is 2. And here the order of this edge permutation is 3. And let's have a look at this here. So the more complicated sequence of moves, we have a 7 cycle, a 2 cycle, a 2 cycle, and a 1 cycle. So here you have to take the least common multiple of 7, 2, and 2, which is 14. And as for the corners, you have a 3 cycle and a 5 cycle. And the least common multiple of 3 and 5 is 15. So you see that the order of the corner permutation is 15, and the order of the edge permutation is 14. And this is, by the way, exactly what we have observed in the previous video, where I just did this experimentally, but now we have actually also a mathematical proof that this is the case. So let's bring this all together, what we have up to now. So we have realized that every sequence of moves on the Rubik's Cube has 2 permutations, Fe and Fc, and we have this estimate odd of f is at most the least common multiple of 2 times the order of Fe and 3 times the order of Fc. And also we just saw that we can compose both of these permutations here into cycles, and then we can determine the order as the least common multiple of the cycle lengths. So let's say this has cycle lengths n1 to ns, and Fc has cycle lengths m1 to mt. Then we know that the order of f is at most the least common multiple of 2 times the LCM of these numbers and 3 times the LCM of these numbers. And also we saw that these numbers add up to 12, and these numbers here add up to 8. And of course we always may rearrange these cycles in a certain order. It doesn't matter in which order we put them, so we can always assume, so without loss of generality, we can assume that n1 is less or equal than n2, etc. to ns, and also m1 is the smallest one, etc. So we may assume that these numbers are increasing. Okay, so we have almost reduced the whole problem to a pure number theoretical one, namely we just have to go through all partitions of 12 and all partitions of 8. And then we have to compute this thing here. And then we have our upper bound for the order. If we can prove that this expression here is always at most 1260, we are done. But there's a catch here. Namely, it can be that if we regard these partitions here independent from another, we may achieve here a number which is too high to achieve our desired estimate of 1260. Namely, if we consider the partition of 12 with 1 plus 4 plus 7, and as before 8 is, say, 3 times 5, what do we then get for our expression? So we have LCM of 2 times the LCM of these three numbers and 3 times the LCM of these two numbers here. So these numbers are co-prime and these as well. So the LCM is just easy to compute as the product. And here it's 28 and here it's 15. So you have the LCM of 56 and 45. And this is 2520. So this means that our estimate here is not good enough if we consider these partitions here independently from another. So in other words, if we consider the permutations of the edges and the corners independently from another. So this is not correct in the sense that this is not good enough to achieve our desired estimate that this is at most 1260. And this is where we need to talk about the signature of a permutation. Namely, the thing is that the signature, and I will define it later on, of these two permutations here, FE and FC, are the same. And this is what we didn't include so far. And it turns out that if we take these two partitions here, the corresponding permutations do not have the same signature, meaning that this bad case here won't appear and we are saved. So this is what we need now. Every permutation has a signature called SGN of f, also called the sign of f, which is either +1 or -1. So this is a mapping from the set of permutations to the set consisting just of +1 and -1. So here X is any finite set. And this has very special properties, namely, first of all, if f is an n cycle, then the signature of f is 1 if n is odd, and -1 when n is even. So this means that we can compute the signature of a permutation very easily if we have an n cycle. For example, a 3 cycle has signature 1, a 4 cycle has signature -1. Also, when you plug in the identity, this is always 1, okay? And very important, if you compose two permutations, f times g, the signature of this here is just the product of the signatures. Okay, and this makes it possible to compute the signature of every permutation you can imagine. Because remember, every permutation is a product of disjoint cycles, and then you can just apply these rules here to compute the signature. So for example, if f is this permutation, so it's a 2 cycle, a 3 cycle, and a 4 cycle, we can compute it as follows. So first we take the signature of the 2 cycle, which is -1. Then we take the signature of the 3 cycle, which is +1. And then we take the signature of the 4 cycle, which is -1. So in total, we get here 1. So just 1. So in general, you see that the signature of a permutation decomposed into cycles is 1 when the number of even length cycles is even, and otherwise it's -1. Okay, so this is how you can always compute the signature. So I won't prove to you that actually this mapping here exists, this sign mapping. This is what you would need to take for granted for here, but of course you can just consult Wikipedia, for example, and there you see the proof of existence of this signature mapping. And now we can actually prove this theorem here if we have any sequence of moves in our Rubik's Cube group, then the signature of the edge permutation is equal to the signature of the corner permutation. And we can prove this. So by definition, F is a product of moves like U, D, F, B, R, L. And we know that the signature behaves well with respect to products. Okay? So this means that we can assume, without loss of generality, we can assume that F is one of these moves. Is one of these moves. And it's all the same for every one. So for example, F is equals to U. So what happens here? We already know what happens. It's just a 4 cycle of these edges here. So it's a 4 cycle. So this means the signature is -1. And what about the corners? So we also know it's just a 4 cycle here. So this means the signature is also -1, and we are done. So with every other phase move here, it's the same. So also if I do R, this is a 4 cycle of edges and of corners, so the signature is -1 in each case. And again, because we have this rule that the signature of a product is the product of the signatures, this is enough to cover every product of moves consisting of these phase moves here. So no matter what we choose, the signature here is always the same. And by the way, this now also proves that there's no sequence of moves which just exchanges one pair of edges. Because this would mean a 2 cycle of edges which has sign -1, but the identity on corners which has sign 1. And -1 is not 1. So we see with this theorem that it's not possible to just swap 2 edges. And by the way, you can also then, of course, prove in the same way that you cannot just swap 2 corners. So the T-perm is the best you can get, that you can swap 2 corners and 2 edges here at the same time, because then both permutations have actually signature -1, and then they agree. Okay, and also what I would have mentioned earlier already is the following. So if I have a permutation, so if a permutation has cycle lengths n1 to ns, we can compute the signature of this permutation with this formula here. So we sum up all the cycle lengths, but with -1. So for the proof, we can assume that f is an n cycle, because when f is a product of cycles, we can use that this is here multiplicative and this is also multiplicative. So we can just assume that this is one cycle here, and then we see that when n is odd, then we know that this has sign 1, right? And this power here, this is also 1, because n is odd, so n minus 1 is even. And -1 to the power of an even number is 1. And similarly, when n is even, then the signature of f is -1 and -1 to the n minus 1. In this case, it's -1. So we see that the claim is true when f is an n cycle, and again, we can then deduce it also for every permutation. And now we are finally ready to write down the number theory problem, which we have reduced the whole estimation here. So we have seen this reduction. When f is any sequence of moves on the Rubik's cube, then there are partitions of, say, 12. So again, we may assume that they are increasing here, and also of 8, such that the signatures corresponding to these permutations are the same. So such that, and we have just seen what this means. Right? And then we can give an upper bound for the order. And remember, the goal is that the order of f is at most this number. So we're done if we can show that this expression is always here at most 1260 if these numbers n1 to ns and m1 to mt satisfy two conditions. So first of all, they sum up to 12 and 8, and also the signatures here in terms of these expressions here agree. So this is the number theoretical problem, which we just have to solve now. So we claim this expression is always at most 1260, and it can also be achieved, namely with the sequence of moves we saw before. So we have the decomposition of 12 with 1, 2, 2, 7, and 8 is here equal to 3 plus 5. So there we actually see that this is equal to 1260. Our goal is that it's not possible to go beyond this number. Okay, but in order to verify that this expression is always at most 1260, we need to go through all the partitions of 12, and it turns out that there are actually 77 partitions of 12. Also, we have to go through all partitions of 8, and it turns out that there are 22 partitions. So theoretically, if we want to do this by hand, we would need to check all the 77 partitions of 12 and also all the 22 partitions of 8 and then match them up. So this makes 77 times 22 pairs, which is a lot. Then we need to check this condition, and then we need to compute this expression and verify that it's at most 1260. And this is something which you don't have to do by hand, and probably you also don't want to do this by hand, right? It's better to write a small program for this, and this is what we do next in order to avoid any manual calculation here. Alright, then let's write some code. If you're not familiar with coding, you can just skip to the next section of the video. I will choose Python here, but of course you can choose any language you like. And the goal is to write here some code that verifies that indeed 1260 is the upper bound for all these expressions. So first of all, we will need to write a function which returns the set of partitions, so integer partitions of any integer. So it's a set. I will use typins here as well. And what will be actually a partition, I will realize this as a tuple of integers. So this is the return type here. For example, when I have, let's say, the number 8, then a possible partition could be 4, 4, or 1, 3, 4, or just 2, 2, 2, 2, or 3, 5, something like this. So these are all tuples of integers, and we will get the whole set of all of these partitions So this is then the set of partitions of 8. Of course, you could just use a library for this, but I wanted to make this code self-contained. Then it's also clear that it's true what we do here. Okay, and the idea is actually quite easy. So how do we generate a partition of, say, 8? You just pick a random number between 1 and 8 with which the partition starts. So let's say I take 3. And then what comes is a partition of 5, right? Because you can just bring the 3 here to the other side, and then you have here a partition of 5. So this is the idea. So in other words, we do it recursively. The first case is that the number here is just 0. Then we just have one partition, so return a set which just have the empty partition. So it's the empty tuple in this case, right? In other cases, we will build up all the partitions in a set which I call result. And it starts with an empty set. And now we go through all the numbers from 1 to n. So n plus 1 here because range is exclusive with the last number. Then we go through all partitions of the number n minus k. So set of partitions of n minus k. And then we build a new partition, namely we take the tuple, which is just k, and we append the partition k q. Then we sort it, the result. Otherwise, we will get multiple times the same partitions. So for example, 2, 4, and 4, 2. So if we build a partition of 6, right, and we either decide to start with 2 or with 4, this will produce 2 tuples, but of course we will sort them. So in this case, only 2, 4 will be included in our set of partitions. So this is how we make them unique. All right, but this is a list now, so we need to convert it to a tuple again. And this is what we call our new partition. So this is what we add to our set of all partitions. And in the end, we return the result. Okay, so we can test this. So let's say we want to display all partitions of 8. We do this here. And then let us execute the code. Let me align this to the right here. Now we can execute the main file. And then you see all the partitions of 8. And you can also print the length. So it should be 22 actually. Yeah, 22 partitions. For example, here we have our 3 plus 5. Here we have the 1 plus 2 plus 5, etc. And also here we can now also do the other one, 12. So there we get 77 partitions. And let us also display them. So there are a lot, as you can see. All right, so this is the first step. We have now computed the set of all integer partitions. Okay, next up we have the signature of a permutation. And we already saw that this only depends on the cycle length, which is a partition. So as an input, I have a partition, which is again a tuple of integers. What I get is a number, so either 1 or -1. What I do is what we saw before. I take -1 to the power of a certain sum. What is the sum? Well, the sum of all k minus 1 for k in this partition. So this is the signature. We can also test this. So if I take a tuple here, let's say I take 1, 4, 5. Let me print this. And again, -1. And this is correct because the number of even length cycles here is 1. So it's not even, it's odd. So the sign is -1. Okay, and now we can actually do the main function here. Get highest order, let's call it like this. And I will not specify the return type for now. We can do this later. So what is the highest order? Let's start with 1, and then we will hopefully make it better. And we will also keep track of the best edge partition. So best edge partition, which is a tuple which realizes the permutation of the edges we are looking for. So this is actually, again, a tuple of integers, and we initiate this as the empty tuple here. And then in the same way, we have the best corner partition. Okay, and now we generate all the possible partitions. So the edge partitions, we have the function set of partitions. We input 12. And then we have the same with the corner partitions, which is here with the number 8. And now we do the loop. So for, let's say we call a corner partition in corner partitions, and also for all edge partitions in the edge partitions set here. We first of all check if the signatures are the same. So I call this valid. So this is exactly the case when the sign of the corner partition is equal to the sign of the edge partition. If this is not valid, I just continue in this loop, so I don't want to do anything here anymore. And then I can now compute the order. And we already saw how to do this, so we take the LCM. You have to import the math module here. And then we have the math.lcm function. So this is the least common multiple here, and it also accepts multiple arguments. So this is what we use later. So first we take 2 times the order of the edge permutation, which we saw as the LCM of all the numbers in the edge partition. And here you can spread out these arguments with a star, and here take the edge partition. And now the same with the corners. All right, so this is our order. If we have found a better order, so if the order is higher than the highest order, then we have a new best case, yeah? So we save this as the highest order. This is now our order. And the best edge partition is now the edge partition, and also the best corner partition is the current corner partition. At the end, we return everything which we have found. So we return the highest order, we return the best edge partition, and we also return the best corner partition. So now we can also, if you want to write types here, it's tuple which is returned. The first thing is the order, so it's an integer, and the second thing here are these 2 partitions. So you have twice a tuple of integers here. So this is the return type of this function. And now our main function, where we just execute this function and then we are done. So we execute this function, get highest order. Remember, this is what we get, so we unpack this here. Okay, cool, and then we just print this now. So something like the highest possible order is, and now let's print it here, highest order. And I also want to know which partition is actually responsible for this highest possible order. So this is why I kept track of this as well. So the edge permutation decomposes into cycle lengths, or into cycles of lengths, and now we can input our edge, best edge partition. And here the same with the corners. So the corner permutation here, we take the corner partition. Okay, and now we just do the usual thing. So if name is equal main, we execute our main function. So when we now run our Python file, let's clear the console here. We should actually get the desired result. And here we go. The highest possible order is 1260. The edge permutation decomposes, let's make it a bit bigger here, decomposes into cycles of lengths 1, 2, 2, 7. And the corner permutation decomposes into cycles of lengths 3 and 5. And maybe you remember that our move sequence, which we have examined before, which actually has order 1260, it has exactly this cycle decomposition. So this is actually also true that this is the unique one. So if you want to keep track of all the possible edge partitions and corner partitions which achieve this highest order, we can also do this here. Yeah. So if we are here, let's do a check if the order is 1260. Let's print the best edge partition and the best corner partition. Okay. And let us remove this here for now. And then we see that this is only printed once, which means that this is the only way you can achieve the highest order, right? By doing an edge permutation, which has these cycle lengths, and a corner permutation, which has these cycle lengths. What I also want to show you is how many computations are actually done now with this code. So let's introduce a counter. And every time we are in the inner for loop here, we increase it by 1 and just print this counter. And then we can have a look here. And you see a lot of computations are done here, and you don't want to do this by hand. And of course you might think, hey, I can do this by hand because I only need to consider partitions which have very high numbers. So for example, of course I don't consider this partition of 8, right? Where I have this one here. This is correct, but this is not really true with other partitions. And the reason is that the LCM is not an increasing function in its arguments. So it's not enough to consider the partitions of 12 or 8, which have mostly high numbers. This is not enough to guarantee that you find the highest possible order here. This is why you have to really loop through all of them to make this mathematically sound here. All right, and what I also wanted to show you is what happens when I remove this validity check here. So let's comment this out and let's run the code again. And here you go. This is what we observed before. If you don't do this check, you actually can achieve this partition of 12 and this partition of 8. And then the order you get is twice as many as we wanted. So it's not 1260, but rather 2520, which is too high for us. So again, this is why it's very useful to make this check here. And by the way, we can also alter this function here. Let's just copy this function to get the list of all possible orders. Yes, so get all orders. So we don't need to save anything here, and here the order, let me just print it. But on the other hand, we will also have duplicates then, so maybe we only print it if it hasn't been found before. So let's start with a set. And each time we have an order here, we add this order to the set, and only in the end we print the orders. And then maybe let's also sort it. So let's take this as a list here and then sort it and maybe reverse it so that we start with the biggest one. Okay, so let me remove this code here, and now just this one here, get all orders. So this is the set of all possible orders. As I mentioned before in the video, this is not precise because here the multiplication with 2 is sometimes not necessary. But yeah, this is a rough approximation of the possible orders in the Rubik's Cube group. So when you look this up, actually this is the correct sequence of possible orders in the Rubik's Cube group. And what we have done in this video is just to verify that it actually ends with this number here. What's also interesting is the exponent of the Rubik's Cube group. So this is the least common multiple of all the possible orders of the elements, and this is 55,440. And the exponent is a very nice number, namely it means that if you take any sequence of moves on the Rubik's Cube, it can be complex, can be very long, it can consist of 1000 moves, it doesn't matter. If you then repeat this many times, you have restored the cube. So this is the meaning of the exponent. This is not to be confused with the maximal order, because this is only saying that there is a certain sequence of moves which has this order, but it doesn't say that every sequence of moves has an order which is a divisor of this. So this is not the case. No, for this one we need to take this one. But in order to compute this, of course, you have to compute all the possible orders, and this involves some more mathematics actually. But what's interesting is that in our computation here, these numbers are all correct already. Only here in the correct list, the next one is 315, and this is missing here. So this is actually one of these permutations where you don't have to multiply with 2 over 3 to get the corresponding order, because there the edge permutation actually doesn't do the flipping of the edges. Alright, this means we're done here with the code. Of course, you will find also a link to the code in the video description. Okay, let me finish this video with a short remark about higher order cubes. So you can also ask yourself, what about the 4x4x4 cube? And this has been answered in this question, whose link I will leave in the comments. And I've also used this answer here by J-Mary also to make this video actually. So this was about the case n equals 3. But in general, for the n by n by n cube, these are the numbers for the highest orders. Which is interesting is that starting from n equals 6 on, the number doesn't increase anymore. That's quite fascinating. And for n equals 4, you see that the highest order you can achieve is also a very interesting number, because it's repeating here. So it's 765,765. If you know a sequence of moves on the 4x4 which has this order, please let me know in the comments. I'm very curious about this.